Okay, we're going to actually use the Bosavar law to calculate a magnetic field from a current carrying wire. This is one of the most complicated problems we do all semester. Okay, so we've got some current flowing through this finite wire. So we're at some point, we're going to take the limit as A goes to infinity, and we're going to think of this as an infinitely long wire with some current in it. And then, like if you're measuring the magnetic field from a wire in your house, as long as you're close to it, you could pretend like it's infinitely long because its total length is much bigger than your distance from it. So we're doing a lot of mathy hand waving here. Is it possible to have current flowing along some finite piece of wire with nothing else in the universe? No, I mean, I guess you could. You could build a capacitor, maybe. So have charged plates here and then connect them with the wire. And if somehow you could balance everything out so that the current is constant flowing along that wire, then maybe you could build this. But think more of this as a theoretical construct. Somehow we've got a constant current flowing along this finite piece of wire. I want to find the magnetic field a distance x away from the middle of that wire. This problem is going to be one of the hardest problems we do all semester, and we still can only solve this problem along the x-axis. If you wanted me to find the magnetic field out here at some random spot, I wouldn't even know how to do it. Nobody would. It would be too hard of a problem. So we're picking a very special case here. We got a finite wire, currents flowing through it. Right in the middle of the wire, I'm going to come out some distance x, and I want to find the magnetic field here at this point P caused by that current. And we're going to use the Bosavar law to do it. So we're going to do this using differentials, or we could do it using Riemann sums. Either way works just fine. So I've got some little di here. I flows that way. So di is just a unit vector that points in the direction that your current is flowing. If I'm at this little tiny chunk of current there, then my r hat points back toward my point of observation. And b is mu naught over 4 pi, the integral of I dl cross r hat over r squared. This is the formula we're using. I want to do a line integral here. I want to do an integral. You can't integrate over some cross product. You have to actually do the cross product. And remember here, this is a vector integral. We're technically going to be integrating in 3 dimensions here. B is a vector. So what we're going to do is do the cross product, figure out what our direction is, see that it all points in one direction. So this does turn out to be a one-dimensional integral. Then we're going to find the magnitude by taking magnitude of everybody. So this is what we got to worry about first, dl crossed with r. So dl points up, r points down this way. So I'm going to draw that here. Here's negative a, here's a. I've got a little dl that's pointing up. I've got an r hat that points down at some angle. They called it phi. So dl, I point my fingers in the direction of dl and curl towards r. See, I can't do that like this. If my thumb's pointing up, I'm not curling toward r. I'm curling away from r. You want when you curl your fingers like this, you want them to cover that angle. So I'm going away from angle phi there. Now I'm going through angle phi. My thumb points down. So over here at point P, the magnetic field points into the board. Okay. What about if I were down here? So DL still points up. R now will point like this. DL cross R still points down. So we're okay. It's not like whatever's here is going to cancel here. Everybody, every little chunk of current is all going to create a different vector that are all going to add up to point down. So we know B points down. Okay, then we can worry about the magnitude of B because we got our direction. Well, magnitude of a cross product is the magnitude of the products. So take each magnitude. Both of those have unit length. DL is a unit vector in the direction of your current. R hat is a unit vector that points towards your point of observation times the sine of the angle between them. That's the definition of the magnitude of a cross product. Okay, so we got to figure out how to write sine of phi in terms of stuff from the problem. Okay, so we notice here, here's my angle phi. I can build this right triangle here. I'm up some distance y. That's my variable of integration, y. So if I get y's in there, I can integrate that. That's okay, because y is going to go from negative a to a. Here, this is my distance I am away from the line of current, x. And then my distance here then will be square root of x squared plus y squared. That's just Pythagorean. I'm going to use trig to write sine of phi here. And this is the way your book did it, and I like it. Sine of any angle is the same thing as sine of 180 degrees minus that angle. Sine of 30 degrees and sine of 150 degrees are the same. So instead of using this angle, I can use this angle and say sine of pi minus phi. That's the same as sine of phi, but now I can use my triangle. Sine will be opposite over hypotenuse. So my double integral, or my single integral here, magnitude of B will be mu naught over 4 pi integral from negative a to a. I, that comes out because I was a constant. That was 1, that was 1. I get x over square root of x squared plus y squared over r squared. So times another 1 over x squared plus y squared squared dy. So dl here is magnitude of dl, which is 1 dy. Okay, now square root of x squared plus y squared times another 2 of those, mu naught I over 4 pi negative a to a will be, I have, that's 1 square root and 2 more square roots. That will be x squared plus y squared to the 3/2 power. So this is the integral I have to do. It's very common on these, the Coulomb law problems we did, several weeks ago, and these Bosavar law problems to end up with something raised to the 3/2 power. That happens a lot. And it comes from having that r hat there and having an r squared there. Remember, we got a 3/2 when we found the electric field from a line of charge. We did the same problem with an electric field from just having a line of stationary charges, and we got a very similar integral. This is kind of the analog to that problem. So now we just got to do this integral. Notice we're integrating with respect to y. So x here is a constant. Okay, so we're going to look up our table of integrals. And the only one we have that has a 3/2 to the as our exponent in the bottom is this one. But we got to be very careful here because this is dx. So I'm going to take this and rewrite this in terms of u, and then we'll rewrite it in terms of y. So this says the antiderivative of du over a squared plus u squared to the 3/2 is is u over a squared square root of a squared plus u squared. Because I'm about to turn all these x's into y's, and I don't want you to get confused. So that's from our table of integrals. This is what I have. So u and y are playing the same role here. X and a are playing the same role. I'm integrating with respect to y. So that x is a constant. It just comes along for the ride. So I'm going to bring along that x. I'm going to pick up a u on top. U here is being played by y. I pick up an a squared in the bottom. That will be an x squared. And then times square root of x squared plus y squared. And one of these x's cancel. So I get y over x square root of x squared plus y squared. But remember, we were integrating that from negative a to a. So this thing, b then, will be mu naught I over 4 pi y over x square root of x squared plus y squared, evaluated from y equals negative a to y equals a. And by symmetry, in the bottom, I get the same thing whether I plug in a negative or a positive y, a. On the top, then I'll get a minus negative a, we get 2a. So that gives us this formula. So your book just jumps straight from here to here. I thought it was important to go through those details. So here's the magnetic field. Caused by a finite line of charge that's 2a long, a distance x away. So I'm going to write this down because now we're going to play a game with this. Mu naught I over 4 pi 2a over x square root of x squared plus a squared. Now, we want to know what happens if we have an infinite line of charge. So we're going to take the limit as a approaches infinity. So, like your naive notion is, top goes to infinity, bottom goes to infinity. Something we can get that a to cancel possibly because they're both really linear in a. That's an a. Square root of a squared is an a. It's possible to make those a's cancel out and take the limit. So that's what we're going to do. We're going to factor out this a squared from out of this radical so that we can get our a's to cancel. So this will equal the limit as a approaches infinity, mu naught I over 4 pi 2a x. I'm going to pull out an a squared. We did the exact same thing with Coulomb's law in an infinite line of charge. I'm going to do this, square root of a squared, square root of x over a squared plus 1. So you'll have to convince yourself that I factored out that a squared properly. I just divided both of these by a squared and then just wrote that in front. You could redistribute it and check it. Square root of a squared is a, that cancels that a. And then I want limit as a approaches infinity of mu naught I over 4 pi 2 over x square root of x over a quantity squared plus 1. This limit I can take, and it's easy. That thing right there, as a goes to infinity, x over a goes to 0. That part approaches 0. 0 plus 1 is 1. Square root of 1 is 1. We get this. I've taken the limit, so I don't have to write limit anymore. And then that 2 cancels. We get mu naught I over 2 pi x. We are going to get this exact same result on Thursday using Ampere's law. Like literally the last 10 minutes, probably it took me to do this problem. The hardest problem we do all semester. I'm going to do the same thing using Ampere's law, and it's going to take less than a minute. Ampere's law is incredibly powerful. It's like Gauss's law. It's, in my opinion, it's the analog to Gauss's law for magnetic fields. It's not really, because remember, Gauss's law for magnetic fields is through any closed surface, the flux, the magnetic flux through that surface is 0. That's actually Gauss's law for magnetic fields. Ampere's law, though, those problems look like Gauss's law problems from electric fields. So what does this say? This says the magnetic field of an infinite line of charge drops off like 1 over distance. So if I have an infinite line of current, I said charge, I meant current, an infinite line of current, then the magnetic field goes in circles around it, goes like this. Behind the board, it's going that way. Here on top, it goes like this. Over on the side, it goes in. So all down here into the board, all over here on the surface of the board, the magnetic field would be pointing out, and it drops off like 1 over distance. If I double the distance, I get 1/2 the magnetic field. Okay, and yeah, that's this picture here. And remember, I literally just said that there's Gauss's law for magnetic fields. The flux through any closed surface is 0. Okay, what if we have 2 wires? So I've got this wire here that's coming out at your eyeballs, and this one is going in away from your eyeballs. Both of those create magnetic fields that spin in lines. And the easiest way to do that is to use the right hand rule. Anytime something's going straight, your thumb goes in the direction of straight. So I've got this current here. Let's call him I1. Here's another one going into the board, I2. It's a straight wire. It's coming out at you. Then point your thumb that direction. Your fingers, you got to do this motion, will curl around the wire like this. So his magnetic field lines don't start and end. Magnetic field lines don't start and end. They'll look like this. His magnetic field lines. He's going in, so my thumb points in and my fingers will curl around like this. So his magnetic field lines will go in circles around him like this. And again, if you go double the distance, you'll get 1/2 of the magnetic field in magnitude. So here in the middle, in between the wires, the magnetic field on both of them point up. Those are combining together. But out here, see this guy's creating the blue lines. This guy's creating the black lines. Out here on the outsides, they'll kind of cancel out. They won't perfectly cancel because we're closer to him over here, so forth. But they tend to cancel a little bit. We're going to do a similar problem to this later with a coaxial cable. You guys know what a coax cable is? Like what your cable modem line comes in. You got all that like fuzzy wire here and then that center wire here. The way that works is current flows one direction through that center wire and the opposite direction the other way. And there's a reason for that, because the magnetic field from this guy and from that guy will cancel out here. That's why we use coaxial cables, so that this is shielded. This does not create a magnetic field that's going to mess up your electronic equipment that sits beside it. Similarly, RCA cables, your stereo cables. I know you guys probably don't own stereos anymore, but stereo cables are designed for magnetic shielding. These guys here. Currents flow in two different directions to cancel out some of the magnetic field. Okay, we're about a third of the way through this chapter.